Hi, my name is Alexander Renz-Wieland and I will present our work on dynamic parameter allocation in parameter servers. Let me start with a summary of the key points of our work. Distributed training is essential for large-scale machine learning tasks, and the key challenge in distributed training is managing communication overhead. We study parameter servers. Parameter servers are intuitive to use and available in many systems, but they lack support for common techniques to reduce communication overhead. In our work, we investigate how parameter servers can support such techniques and whether such support would be beneficial. We find that a parameter server can directly support such techniques if it can relocate parameters during runtime. We also find that the support can be highly beneficial. It can improve performance by up to 2 orders of magnitude and provide near linear speedups. Now let me discuss these points in more detail. Distributed training has become a necessity for large-scale machine learning tasks. It allows you to use datasets and models that exceed the capacity of a single node. And it also allows you to train faster by using distributed compute. Parameter management is a key concern in distributed training. All nodes read and write the same parameters, so the parameters have to be synchronized among the nodes. Parameter servers are widely used to do this. A parameter server is a key value store that is specialized to machine learning. It provides primitives to read and write parameters and takes care of partitioning and synchronization in the background. This makes it significantly easier to implement distributed machine learning algorithms without low-level programming. This is why parameter servers are used as a component in many machine learning systems, for example, TensorFlow and MXNet. Logically, you access one global parameter server, but physically parameters are usually partitioned to a couple of nodes. Usually these nodes coincide with the nodes that host the worker threads, such that for each worker thread there is some local parameters. A key challenge in distributed training is the communication overhead. I brought you an example here where this is a knowledge graph embeddings task, and we use 1 to 8 nodes, and we measure the runtime of one epoch that in PSLite. PSLite is a common parameter server system, and you can see on a single node it takes 4.5 hours, and on 8 nodes it takes 1.5 hours. So there's a 3 times speed up from 1 to 8 nodes. Now, an important point is that PSLite is not efficient on a single node, and this is because it accesses parameters via inter-process communication. You can do better. So if you access parameters over shared memory, the single node performance improves dramatically. So we did this, and with shared memory access, the performance on a single node is 1.2 hours. So now PSLite on 8 nodes is slower than the single node. In the following, we will look at how you can do better, how you can scale from this stronger single node performance near linearly. Key to do this is to reduce communication overhead, and distributed machine learning algorithms use techniques to do so. 3 of these techniques are the following. First, data clustering. The idea is that you cluster your training data and you partition the data according to this clustering. And then you allocate the parameters where they are accessed most frequently, such that the majority of parameter accesses can happen without network communication. A second technique is parameter blocking. In parameter blocking, you split an epoch into multiple sub-epochs, and in each sub-epoch, you restrict each worker to a subset of parameters. And then from sub-epoch to sub-epoch, you switch these restrictions. And in each sub-epoch, you allocate the parameters where they are accessed. A third technique, latency hiding, is a standard technique where you prefetch parameters asynchronously before they are used, such that the actual access does not require synchronous network communication. All these techniques have a common key, and that is to avoid remote access. Now, we looked at whether parameter servers can support these techniques, and what we found is that these techniques require local access or fast access at different nodes over time, but parameters cannot provide this because they allocate parameters statically. So we asked what the situation would be if the parameter server could allocate parameters dynamically. That means if it had the ability to relocate each parameter during runtime. For example, it could provide a primitive to do this that allows the application to request a relocation of a parameter. Now, this would provide support for the three techniques that we just discussed. For example, in parameter blocking, you could relocate the parameters during two sub-epochs. Or for latency hiding, you could relocate a parameter slightly before you will use it, such that it is local when you use it. And then you do nothing else. You just wait until another node will access this parameter, and at this point you will move it to the next node. So this technique or this ability is what we call dynamic parameter allocation. The ability to relocate parameters during runtime. We implemented this capability in a prototype system which we call Lapse. Lapse, let me highlight some of the key features of Lapse. First, it provides dynamic allocation, obviously. And second, it provides location transparency. This means the read and write operations of the parameter servers work regardless of what the parameter is doing in the background. So it does not matter where the parameter currently resides. It does not matter whether the parameter is currently relocating. And the third key feature is that Lapse retains the sequential consistency of classic parameter servers or common other parameter servers. So for example, a typical parameter server provides sequential consistency but not serializability, and Lapse provides the same. This is a big difference to other parameter servers that provide, or other stale parameter servers. These usually provide only some form of bounded staleness sequential consistency. Yeah. But Lapse can provide what other parameter servers do. So this creates many system challenges. For example, you have to manage parameter locations, you have to route parameter accesses to the current location, and you have to do all of this while you maintain sequential consistency. I will not discuss these challenges further. They're discussed in the paper. Instead, let's look at some experimental results. We ran an experimental study on 3 different machine learning tasks: matrix factorization, knowledge graph embeddings, and word vectors. And we used a cluster of up to 8 nodes, each node with 4 worker threads and a 10 gigabit Ethernet connection. We did 5 things. First, we studied the performance of classic parameter servers, and our key finding is that 2 to 8 nodes barely outperformed a single node in all the tasks that we tested. And the second point that we investigated was the effect of dynamic parameter allocation, and where we found that this can be up to 2 orders of magnitude faster than classic parameter servers and provide up to linear speedups. So at the bottom, you see the same graph that I showed you earlier, the training knowledge graph embeddings. And you can see these 2 points. First, PS-Lite does not outperform the single node performance. And second, Lapse is significantly faster and provides near linear speedup with a speedup of 6 times here, roughly. The third thing we did was we compared against bounded staleness parameter servers. Here you see the runtimes for matrix factorization on a large matrix using the parameter blocking technique to reduce communication overhead. And so first thing you see is that Lapse scales linearly here, even slightly above linearly. And then I want to highlight 2 points about the bounded staleness parameter server. So we use ptoom here. Ptoom is the most common bounded staleness parameter server. And we use 2 variants here, client synchronization and server synchronization. They differ in how replicas are refreshed. So you see 2 points here. There's a single node overhead. This comes from how ptoom accesses local parameters. And then an important point is that ptoom does not scale linearly. Now, we did 2 more things. We compared to manual management and found that Lapse is competitive to a low-level implementation. And we did an ablation study where we found that for the performance, it is crucial that you combine fast local access with dynamic allocation. So to wrap up, we saw that machine learning is a key challenge in distributed machine learning. Parameter servers are intuitive to use, but existing ones lack support for common techniques to reduce overhead. And you can add the support if the parameter server supports dynamic parameter allocation. And this support can be highly beneficial. It can improve performance of up to 2 orders of magnitude. This source code of Lapse is open source, so feel free to check out our code. Thank you. Thanks.